Pressing record. If somebody could make sure I press record, and if somebody could also make sure that the little audio bars are moving when I press record, that'll be great. There have been a number of times when I press record a whole lecture, and it's silent because the mic wasn't on. That's all fun. Okay, well, what we're going to talk about now is going to set the stage for the whole semester, so pay attention. Behold, the carbonyl compound. Our group is generally something that's alkyl or maybe a benzene ring, and the Y thing can be any number of things, but we'll call this a carbonyl compound. And its reactivity is governed by a few simple principles, some that are easy to understand that you may have dealt with before, others that may be a little bit new to you. So one of the simplest ways to think about the reactivity of the carbonyl compound is through the concept of resonance. You should be comfortable by now with the fact that resonance means an alternative way of drawing a Lewis dot structure. When you have two resonance structures, it's not like one is correct and the other is incorrect. You've got to follow the rules for Lewis dot structures, but they are both incomplete descriptions of the molecule. Recall that in resonance, a pair of electrons is not hopping back and forth to different locations. It is simultaneously in both locations. So what you can infer to generate the resonance structure on the right from the one on the left, we've simply taken the two electrons in the carbon-oxygen pi bond and we've moved them out onto the carbonyl oxygen. That suggests what to you about the carbonyl carbon versus the carbonyl oxygen? I'm hearing some partial something or others. Is that okay? So that the carbonyl carbon should have a partial what on it? Positive. That means, in general, resonance tells us that the carbonyl carbon is electron poor or electron deficient, whereas the carbonyl oxygen is what? Should be electron rich. And I typically don't love these hybrid structures where you attempt to draw something like this with a dotted line and a delta minus and a delta plus there. That's fine if you want to do that. I like to just draw the two different resonance structures. But you expect, from what resonance tells you about carbonyl compounds, is they're electron poor on the carbonyl carbon and electron rich on the carbonyl oxygen. That's important because all of what you learned in 351 could be summarized in the first and great commandment of OChem, which is nucleophiles attack electrophiles. You know where a molecule is nucleophilic because by identifying the parts of the molecule that are electron rich, right? So if a carbonyl carbon were going to act as a nucleophile, if a carbonyl compound were to act as a nucleophile, you would expect it to act as a nucleophile at the electron-rich atom, right? So you expect the oxygen to do the attacking if a carbonyl compound is a nucleophile. Similarly, if a carbonyl compound is an electrophile, you expect it to be attacked at the carbon, which is electron poor. Does that make sense? Nucleophiles attack electron poor areas of molecules, and the parts of nucleophiles that do the attacking are the electron-rich parts. Okay? So that's maybe the easy principle. Questions about that? Now, there's a deeper level to this that some of you may have learned, others of you may have not learned. I didn't teach you in 351, so I know my colleagues, I know how they teach, they do an excellent job. I'm not sure if they told you about this or not. If not, I'm going to give you a quick crash course in bonds and orbitals. Do those words scare you a little bit? Let's start by talking about bonds. Rank bonds for me in terms of stability. Sigma bond versus a pi bond. Which is lower in energy? Sigma. Why? Because we learned it that way. Give you a clue. Sigma bonds hold electrons closer to the nucleus. That's a potential energy argument. It's Coulomb's law. Closer to the nucleus you are, the lower you are in energy. Same thing with gravity, right? So pi bonds are held above and below the axis between two atoms. They're further away from the nucleus. They're higher in energy. So if we were to rank bonds in energy, just this little axis here, I would put a sigma bond here and a pi bond here, okay? What about lone pairs? Where do they rank in terms of energy relative to, say, a bond? Higher. Good. How can you tell? It just makes sense, right? It's because they're not involved in a bond. Remember, bonding is stabilizing. Bonding allows two electrons to experience two nuclei. That's a potential energy argument. Second, bonding allows two electrons to spread out more than they otherwise would. That's actually, for reasons we won't talk about, that's a kinetic energy argument. In any case, bonding is stabilizing, so electrons not involved in bonds are automatically higher in energy than electrons that are involved in bonds. Does that make sense? So I'm going to just put lone pairs up here. But I will also put, we're thinking of, in this sort of list, bonds and orbitals. I'm going to write here, it won't come up much in this class, but I'm going to write it here for completeness, empty p orbital. An empty p orbital is an atomic orbital that's unoccupied. You've seen that before in a carbocation. You learned about carbocations, right? You'll learn that that carbon is sp2 hybridized trigonal planar. There's an empty p orbital on the positively charged carbon. It's about the same energy as lone pairs would be, okay? One thing so that maybe most people get that kind of insight from 351. Any questions about that? Yeah?
Our professor likes to talk a lot about like sigma star, pi star.
Yeah, that's where I'm going. Yep.
But it's not the same as like, we wouldn't say that is lone pairs and...
No, so the question is that you've heard about orbitals called sigma star and pi star before. Is that the same as a lone pair? No. We'll talk about what that is in just a second. Sigma bonds and pi bonds are also sometimes called bonding orbitals. They are lower in energy. In general, atomic orbitals of any kind, lone pairs or empty p orbitals, are intermediate in energy. We call them sort of non-bonding because they're not involved in bonds. Now, one of the things you may not have heard about, and we don't have a huge amount of time to go into this. If you want to know more, there's an excessively long molecular orbital theory review study guide, totally optional. You can look at it or not. But if you want to know more, you can take a look at it. We'll explain where some of this comes from. But to be short in speaking, what I will say is every bonding orbital is associated with an empty antibonding orbital. So just for fun on this diagram, I'm going to use two little lines to indicate that it's a bonding orbital and it has electrons in it, right? Does that make sense? So two electrons in a sigma bond. This isn't a diagram for any particular molecule. We're just being as general as we possibly can. Here's two electrons in a pi bonding orbital. You've seen what that looks like, by the way, right? You've seen, if we were to draw what the pi bonding orbital looks like for, say, a carbon-oxygen pi bond, what would we see? It looks like we could draw it schematically by showing you two p orbitals, one on the carbon, one on the oxygen, and we would add them together with the same wave function sign. We got to back up on that for just a moment. You've seen a p orbital before, and you've seen people draw it like that, right? Do you have any idea what the shading means? Sort of just always done that way. It has nothing to do with charge. It does have to do with mathematical sign. Orbitals are actually mathematical functions, like a sine wave. They can have positive magnitude or negative magnitude. That positive or negative magnitude has no real physical meaning. It doesn't mean charge, so to avoid confusion, we use shading. It doesn't matter which side is positive sign versus negative sign, just that they're opposite. There is a phase, so sometimes people refer to the mathematical sign of the wave function as the phase. It's literally the same thing as a string vibrating on a guitar. It's positive on one side, negative on the other, and goes through zero. Anyway, to make a bonding orbital, we bring two atomic orbitals together side by side with the same wave function sign, and we get this pi bond, which we can draw like that, but if we were to actually visualize what it looked like, when combined, it would look like this. And an electron in that pi bonding orbital isn't hopping from one side to the other. It's simultaneously in all of the space drawn. Okay? That maybe is review from your very first days in 351. And as I said, if you want to know more, go look at that introductory study guide. The point is that for every bond that we have in an organic molecule, there is an empty antibonding orbital. We don't have a lot of time to say more than that, but you can look that up in the MO theory study guide. So, and it turns out in general that the antibonding orbitals are ordered in energy exactly opposite of how the bonding orbitals are ordered in energy. Again, there are reasons for that we don't have time to talk about. So I'm going to draw a pi with a star on it here, and that is the antibonding orbital associated with the pi bond. And there should also be sigma star antibonding orbitals associated with each sigma bond in a molecule. But importantly, notice that the pi star is lower in energy than the sigma star. Okay? If I were to draw for you what the pi star antibonding orbital looked like, all you would do is draw the carbon and the oxygen of the carbonyl molecule. You draw a p orbital on one of the carbon, a p orbital on the oxygen, and then you would use color or shading to indicate opposite wave function sign on one side. In the pi star, notice how in the pi bonding orbital, the wave function signs were side by side, lined up with each other. For the antibonding orbital, it's actually exactly opposite. Okay? What does that mean? That means that the pi star wave function goes through zero in between the two nuclei. There is something called a node. Okay? A node is a place where the magnitude of the wave goes through zero. You can think of it like destructive interference between two waves. If any of you are guitarists, you know a little bit about this. You know how you can pluck a guitar string and then tap the guitar at the 12th fret and you still hear an overtone. That's because you've silenced the major harmonic, but you tapped at a node of one of the higher harmonics and the wave survived. I'm probably not making any sense. A node is a place where the wave function goes through zero, and antibonding orbitals are characterized by nodes in between two atoms. Okay? So that's what the pi star antibonding orbital looks like. Questions about that? Go ahead.
Could you also show the sigma star antibonding?
Sure, if you want to see a sigma star, it would depend on what kind of sigma bond you were talking about. If we wanted to go really easy, we could go a hydrogen-hydrogen sigma bonding orbital. That would look like this, sort of like two 1s orbitals lined up together with the same wave function sign. A hydrogen-hydrogen antibonding orbital would look like this, two 1s orbitals lined up together, opposite wave function sign with the node in between. If you wanted to see a carbon-carbon sigma bonding orbital, here's what it would look like. Depending on the hybridization of the carbon, you might have, it would look like an sp3 orbital on one carbon overlapping with an sp3 orbital on the other carbon. So you can sort of see there the big lobe of an sp3 orbital on one carbon overlapping end to end with the big lobe on an sp3 orbital on the other carbon. A carbon-carbon sigma star might look like something like this. There would be a node in between. There would be two small lobes, two small orbital portions with opposite sign pointing toward the node, and then there would be larger lobes pointing away. That's what a carbon-carbon sigma star antibonding orbital looks like. For the most part, what will be enough for you today now in this class is to understand what a pi star is. It is an antibonding orbital associated with the carbon-oxygen pi bond. Okay? Other questions? Yeah?
Does the star indicate that there's no electron density in it typically?
Yeah, the star indicates that it's empty, that it's antibonding. In stable organic molecules, the bonding orbitals are all filled and the antibonding orbitals are all empty. Importantly, what do you think happens if you were to fill an antibonding orbital? Turns out you cancel out the benefit of the bond and you break the bond. Okay? The simplest demonstration of this is in the molecule hydrogen itself. If we were to think about, I've already shown you what the sigma and sigma star orbitals for hydrogen look like. So here's the sigma bonding orbital. Here's the sigma star antibonding orbital for H2, which we can draw like this. 2 electrons in a bonding orbital, an antibonding orbital that's empty. What happens if I promote an electron using light or energy of some kind, promote an electron from the bonding orbital to the antibonding orbital? I cancel out the energetic benefit of the bond. The bond is the fact that 2 electrons that used to be much higher in energy, one of the things I haven't shown you here is basically the level of what an electron in an isolated 1s orbital would be. The whole point of a bond is the electrons get to be lower in energy than they would have been on an isolated atom. You cancel that out completely by promoting an electron to an antibonding orbital, and so the bond breaks. Okay? And this is generally true. If you fill an antibonding orbital in organic chemistry, you're going to break the bond. Now, maybe you're getting an inkling of where we're going. Let me just say one more thing about the pi star. Because carbon and oxygen are different, oxygen's more electronegative than carbon. The pi star and the pi bonding orbital are a little bit distorted from what I showed you. Oxygen's more electronegative. That means electrons on oxygen are more stable than electrons on carbon are. So the filled pi orbital for a carbonyl group is biased, it leans a little bit towards the oxygen. I drew it before as like it was sort of a hot dog bun, evenly spaced on one side or the other. That's true for a carbon-carbon bond. For a carbon-oxygen bond, it's not true. It's biased a little bit towards the oxygen because, as I said, oxygen is more electronegative. That's my symbol for electronegative than carbon. And electronegativity literally means the electrons on oxygen are a little bit more stable. So it's favorable for that bonding orbital to be biased towards the oxygen. Correspondingly, it's favorable for the pi star in a carbonyl molecule. The carbon-oxygen pi star is biased towards carbon. So if you were to draw this more realistically, what I would show for this orbital is actually a larger orbital on the carbon and a smaller portion of the orbital on the oxygen. Maybe sort of exaggerated the way I've drawn it, but the pi star is more on the carbon than on the oxygen. That's important because it's gonna go with and reinforce what resonance told us about the reactivity of carbonyl compounds. Okay, so we now know that if you look at a carbonyl molecule, if we were to redraw our carbonyl molecule here, it's got some lone pairs. We're not saying what the R group or the Y group is. Here's electrons in the sigma bonds, here's the electrons in the carbon-oxygen pi bond, here's the electrons in the lone pairs. Remember, we're not being too specific, there's multiple sigma bonds, there's multiple lone pairs. You can see from this energy diagram that the most reactive electrons in this molecule, the ones that are highest in energy, are the lone pairs on the oxygen, right? So if this molecule were going to be a nucleophile, you would expect the lone pairs on the oxygen to do the attacking. That's exactly what resonance told us up here, by the way, right? That the carbonyl oxygen was electron rich. Are you seeing the agreement between those two ideas? Okay, now notice our energy diagram for the carbonyl compound, this sort of general thing. The lowest energy orbital that's empty, the lowest energy empty place to put new electrons in this molecule is the pi star. Everything else is filled below. The sigma bonds are filled, the pi orbital's filled, the lone pairs, of course, are there and they're filled. So if in a nucleophile were going to attack this molecule, the only place it could put its electrons would be in the pi star, right? And where is the pi star? Mostly on the carbonyl carbon, which is exactly what resonance told us when we said that the carbonyl carbon is electron poor, okay? Why are we spending so much time on this? Because knowing there's two key skills you're going to need to be successful in this class. Number one, focus in on what's important. Number two, generalize. And maybe number zero, because it should have come in before focus on what's important. Identify what's important in the first place. If you can identify what's important about a molecule and focus in on it, that will allow you to generalize to unfamiliar situations. What we've just talked about describes the reactivity of all the molecules you're going to encounter for the next month and a half, maybe 2 months. If you can get this pattern down, you'll see everything we're going to talk about as variations on the same theme. If you can't, you're going to be scrambling to account for all of the details without any sort of unifying principle. You can't memorize your way through the course. You can try, but you'll be frustrated. It's better to try to understand the basic principles. So, let's give you an example of what I'm talking about. Of a carbonyl compound acting as an electrophile. Okay? And here is some general nucleophile, something that has a high energy pair of electrons. Now, you can do what we're going to do now using either of the explanations that I've just provided about carbonyl reactivity. That is, you can do this either based on what we talked about for resonance or also what we talked about for molecular orbital theory and what the pi star is. Okay? The nucleophile, resonance would tell you that the nucleophile should attack the carbonyl carbon because that's where the partial positive charge is. Okay? So we'll draw an arrow with electrons attacking the carbonyl carbon. Now, Lewis dot structures say the arrow says I just made a new bond. I can't have 5 bonds to carbon because of the octet rule, so I got to do something. And so that would suggest I have to break the pi bond and move the electrons out onto the oxygen. Alternatively, I could have drawn this arrow straight towards the positive charge in that resonance structure. Either set of arrows is okay, because neither resonance structure is correct or incorrect. They're both incomplete descriptions of the same molecule. Now, let's repeat all of that, but let's do that from the perspective of what a nucleophile sees when it attacks a carbonyl compound and where its electrons can go. Let's draw the pi star on this carbonyl compound. So what I drew for you before, I abbreviated. We were looking at a carbonyl compound on the side from its, if all of these carbon, oxygen, CR, CY bonds are all in the plane that I've indicated, then the pi star is above and below that plane, and it's mostly on the carbon, and there is a node in between the two atoms. Okay, this is important. The stuff that's I'm coloring now in gray is the plane that we're talking about. These two lobes are above that plane. These two lobes are below that plane. There is a node in between the two nuclei. If we were to draw this pi star looking down on this molecule from above, what we would see is a large lobe on the carbonyl carbon, a smaller lobe on the carbonyl oxygen. Let's make the one on the carbonyl carbon pink, the one on the oxygen orange. Let's have a node in between the two nuclei. Below the plane of the page, there would be two other lobes that we can't see very well. I'll just give you a hint of one of them here and the other there. Okay, that's the top-down view of the pi star. The nucleophile attacks the pi star at the carbonyl carbon, because that's where most of it is. And when you fill a pi bonding or pi star antibonding orbital, the pi bond has to break. Okay? Anytime you dump electrons from a nucleophile into an antibonding orbital, two things happen. Number one, you make a new bond. Number two, you break the old bond. All right? So this idea of looking for the pi star of the carbonyl compound is important, because that's going to help you to remember that the nucleophile attacks at the carbonyl carbon and you break the pi bond. Okay? Questions? All right. Now let's get a little bit more specific by examining the influence of what this Y group is. Actually, before we do that, let's actually draw the product or the intermediate that happens once the nucleophile attacks the carbonyl carbon. As I said, arrows are the instructions for drawing the next molecule. An arrow from lone pair electrons on the nucleophile to an atom means new bond is forming. An arrow from the pi electrons to the oxygen means a bond is breaking. So, to draw that structure, we'll keep everything else in place. The oxygen should have now a negative charge on it, and then here, I'll use red for that, is our new bond with the nucleophile. And maybe I'll use red for the lone pair that's now on the oxygen. We call that a tetrahedral intermediate. For reasons that we'll talk about a little bit later, in part because the geometry of the carbonyl carbon changed, right? It used to be sp2 hybridized trigonal planar. Now it's sp3 hybridized tetrahedral. So we call it a tetrahedral intermediate. This is a universal feature of carbonyl chemistry. We haven't done any reactions other than this one yet, but you'll see this show up again and again and again. All right. With that, go ahead.
Looking at the orbital, so if we look at the other resonance structure, what is the absence of lone pairs or the presence of actual lone pairs look like with the whole the packing?
Okay, you're saying if I were to try to take the orbital picture here.
Yeah.
Well, I guess it's a good question, though. I would say what you're running up against here is the fact that resonance. The orbital picture for these two would be exactly the same. It's just that we've drawn where the electrons are differently. So if you want to, we could draw, well, I'm trying to figure out how to answer that in the best way possible. The MO picture, because these two are the same molecule, the MO picture for both of them has to be identical. The only difference is we've moved around where the electrons are, whether they're in between the carbon and the oxygen or whether they're on the oxygen. These two resonance structures basically reflect the two things that I told you about both the pi and the pi star. I told you that the pi star was mostly on the carbonyl oxygen. I also told you, our carbonyl carbon, I also told you that the pi bond, if we were to do the same drawing, is biased towards the oxygen. So the pi bonding orbital looks like this. In some ways, the pi bonding orbital, so if you take both of these pictures of the pi bonding orbital, and then the pi star, they both summarize both resonance structures. This resonance structure gives you the idea that the electrons that are in the pi bond are actually leaning towards the oxygen. And this orbital picture gives you the idea that there's a significant amount of positive charge on the carbonyl carbon. All right, others?
With
Yeah.
the nucleophile attack, and I understand this question probably comes from my lack of understanding with pi antibonding orbital, but how can we know which side of the pi star, or not on like the, I'm referring to just the carbon.
That's a great
Which
question.
side, the purple or yellow?
Great question. So the question is, you've noticed the pi star is both above the plane and below the plane of the page. Is one side favored or not? The answer is no. Attack can occur from either side with equal efficiency. What that means is we're getting ahead of ourselves, but notice that if R and Y and the nucleophile are different, we just made a stereo center. The fact that you can attack a carbonyl with equal efficiency from above or below is the same thing you learned in 351, where a carbocation can be attacked from above or below, and you're going to get both configurations. Yeah. Yep, good. What else? Yes?
So we learned that nucleophiles attack electrophilic atoms, but in the case of the anti-bonding pi orbital, it looks like the carbon would be more electron rich. Therefore be more nucleophilic.
So remember, yeah, the question is about why are we attacking the carbonyl carbon, because there's more pi star orbital on the carbon. Remember, the pi star is empty. There are no electrons in it. So you're attacking the empty orbital in the place where it is emptiest. Okay, what else? All right, good. So now we need to try to investigate what role this Y group plays in how reactive a carbonyl carbon is. Okay? There are two main considerations for how the Y group affects carbonyl reactivity. So two basic questions. Is it a good electron donor? And that may be a new concept for you. And then the second question is it a good leaving group? That should be a more familiar question to you. In 351, you learned all about good leaving groups. You learned in the acid-base chapter that good leaving groups are conjugate bases of strong acids. So your pKa intuition is going to continue to be important in this class. So let's talk about what makes something a good electron donor and what makes something a good leaving group. Again, for good leaving groups, we'll start with that one because it's the most familiar. Good leaving groups are conjugate bases of strong acids. So let me give you a short list of good leaving groups. Cl minus, right? Or Br minus. Cl minus has a conjugate acid, HCl, and the pKa of HCl was something like -7. I think for HBr was something like -9. That's a good leaving group. What about water? Well, water's conjugate acid is H3O, whoops, making stuff up here, H3O plus pKa -2. And there are other decently good leaving groups in organic chemistry. For example, negatively charged sulfurs, they are called thiolates, have conjugate acids that are called thiols, and they have pKa's in the range of 8. Other potentially good leaving groups in organic chemistry are called carboxylates. These are conjugate acids, these are conjugate bases of carboxylic acids, which you learned about in chapter 2 of 351. These have pKa's in the range of 4 to 5. Something about that is making me want to just put them in order, because that makes me feel better about the world. So there we go. Other good leaving groups that you will encounter this semester that may be a little bit unfamiliar to you include phosphate groups. A phosphate group, let's see how to do this. Phosphate is one of these polyprotic things that you hated from general chemistry, but the pKa of the conjugate acid of this phosphate group here, the monohydrogen phosphate, that has a pKa around 7. So anyway, these are things that are generally good leaving groups. We could even include on the list amines of some kind, NH3 or NRH2 or other varieties of amines. Their conjugate acids are ammonium. I'm not being complete here. You'll have to draw the other conjugate acids if you wanted to. Ammonium ions, which have pKa's in the range of 9 to 11, and they can be good leaving groups too. You'll see all of these as potentially decent leaving groups. Also, you should be aware of leaving groups that are bad. Bad leaving groups include OH minus and OR minus. That shouldn't be a surprise to you. You had a whole chapter in 351, chapter 9 on alcohols, ethers, and epoxides, where the major theme of that chapter is, if you wanted to do chemistry with alcohols, you had to first turn the OH into a good leaving group, right? So OH minus and OR minus are generally bad leaving groups. Also, NH minus, NH2 minus, NRH minus, and so on are also bad leaving groups. Conjugate acid of the alcohol, OH minus is water or alcohol, pKa is around 16, of course. Conjugate acid of NH2 minus is ammonia, pKa around 38. You'll have a pKa table on my exam, so if all of this is you're stressing out that these numbers aren't coming to you, it's okay. They're not supposed to. I've just been teaching this class for more than half of the time you've been alive, probably, so it's just in my mind. Identifying good leaving groups is important. And good versus bad is always a challenge. We always mean relative to what? So just put a pin in that, because you're going to see that in some cases, we're going to allow OH minus and OR minus to leave as leaving groups, as long as there's something else, some other factor present. So this concept of relative to what is an important consideration. We're not quite ready to get there, but we will. Okay. Second is I don't know why I started with number 1, is it a good electron donor, versus number 2, is it a good leaving group? Because we should have started with the leaving groups. So I'm saying second, we'll go back to number 1. And is it a good electron donor? It turns out that these things that we've identified as bad leaving groups are good electron donors. And the things that we've identified as good leaving groups are poorer electron donors. And they're actually ranked according to the pKa of the conjugate acid. That is, the Cl is the poorest electron donor, and other groups are better electron donors. Does that make sense? So when we look at the Y group, you should be thinking about what if it were, what if it left, what if it were Y minus, is that a good leaving group or not? And that'll help you know, in addition, is the thing that's the Y group a good electron donor or not? Okay? You can use these considerations to rank carbonyl compounds in terms of reactivity. Let me give you an example in the last couple of minutes. I'm going to introduce an actual organic compound. Two different kinds of organic compounds. This is called an ester, and this is called an acid chloride. All right, let's look at the two Y groups. I'll highlight them in yellow. Let's think about what they are if they were to leave. OCH3 minus and Cl minus. Okay? Cl minus is on our list of good leaving groups, but it is also a poor electron donor. Okay, what do you know about this alkoxide? Is that a good leaving group or a poor leaving group? Well, your real question should be relative to what, but we're hedging on that yet. We're just going to call it in general a poor leaving group, but a good electron donor. We're going to see that that consideration tells us that the acid chloride is a better electrophile than the ester. Okay? The ester is less electrophilic than the acid chloride. Why would that be? To understand that, we need to look at the resonance structure of the ester. In which we take the pi electrons from the carbon-oxygen pi bond and move them out onto the carbonyl oxygen, leaving a positive formal charge on the carbonyl carbon. And then we need to realize that the oxygen of the OCH3 group, which is a good electron donor, has a lone pair on it adjacent to that positive charge. So you would expect a good electron donor to donate electron density into the place where there's positive charge, and you can draw this resonance structure in which you now have a pi bond between the oxygen of the OCH3 or methoxy group and the carbonyl carbon with a positive formal charge on the oxygen. The point here is that electron donation by the methoxy group stabilizes the carbonyl carbon, spreading out the positive charge on the carbonyl carbon, making it less electrophilic, making it less attractive for a nucleophile to attack. Okay? Now, what's going on with the acid chloride? Same thing, only chloride is not as good of an electron donor, so it's a smaller effect. The chloride can't stabilize the positive charge on the carbonyl carbon quite as much, so the chloride stays electrophilic. We're going to talk about that more next time. We'll get into more reactions. Good luck, get cracking on studying, and we'll see you on Friday.